that on. All right, well, thanks a lot. So I'm going to talk about landscape response to normal faulting, and in particular firing the sediment gun. So there's been a lot of work, I would say, in the last 15 years in terms of understanding landscape response to normal faulting. So for instance, in response to, let's say, a normal fault such as this one that might initiate, or for example, change its rate due to fault growth and interaction, we now know that the effect, well, the fluvial networks that detect that change in slip rate respond by basically generating a nick point that propagates up through the catchment over time. And this nick point, and I'm marking it here in the red stars, separates the parts of the catchments that have adjusted or are adjusting to, for example, the change in fault slip rate from the parts that are yet to adjust. And then eventually that nick point will propagate through such that topographic steady state is eventually achieved. Now, much work to start with actually really focused on the extent to which we could use these processes to get tectonics from topography and to understand landscape response times. And that's predictably dependent on drainage area for some form of a stream power erosion law, where, for example, M is a half this exponent on the drainage area. But I want to focus on something slightly different today, which isn't the tectonics from topography part, but actually what that implies about our understanding of sediment supply from normal faults, because this process of nick point retreat fires or triggers a sediment gun. And I want to ask what characteristics it has, how long it lasts, and what controls how it appears. So there's a couple of ways to do this. One is to look at real field examples, and I'm going to show you some of that. But the first is to actually do some numerical modeling, and a number of people have done this. I'm actually going to go back to the beginning and talk about what I think is a really seminal paper that the late Patience Cowie produced in 2006 that I and a bunch of other distinguished people were involved in. And what I really liked about what Patience did in this paper was that she coupled together a physical model of fault growth and interaction with a landscape evolution model and could actually see how catchments responded to fault growth and interaction. And actually it was really interesting, when you looked at the fluvial network that developed upstream of these faults that were developing over time. These could be mapped out, and I'm about to show you a map of some of those catchments. So for instance, this is these catchments that are mapped out and how they've changed over time. And if we put drainage area against time in the model run, then some of the catchments grow, then they lose drainage area due to competition, and then they might grow again and expand. And that's controlled by the temporal history of fault interaction. So one of the key things that these sorts of models show is that drainage network evolution in these rifted settings is strongly controlled by fault growth. And of course, that fundamentally affects the sediment release from catchments. So there's a sediment volume over time as well. So for example, catchment 5, when it shrinks, the volume of sediment is reduces, and then it increases as the faults really start going, whereas catchment 4 in this case grew and then got defeated by the fault, so the sediment supply falls to 0. So understanding this process, at least in a model sense, is really important. And it's not just on a catchment, on the scale of a whole catchment, also within catchments are really important. So that was exciting, that went right through. Let's go here. So if we, for example, have a look at this little catchment here, then even within a single catchment, downstream of this point labeled 2A and upstream of the fault, that's actually where much of the sediment is coming from. So this fault starts to grow. This is throw against time. It's a bit of a lag time, and then the sediment yield just in this area really increases. And that's actually because that's where the nick point is in the model. So the sediment is actually sourced from particular places. So that's kind of cool. But we have to ask the question about how these, whether or not these sorts of models reflect physical reality. And of course, they're predicting volumes, but they really ignore sediment characteristics. And of course, we need real examples to understand timescales, and I'm not dealing with lithology and all of these other things. So that's what I want to now focus on. One place to go to do that is Italy. It's somewhere with lots of amazing normal faults. There's a place where I've worked a lot. Earlier in my career, particularly in the central Apennines, and most lately in Calabria with a former student of mine, Duno Roda Beluda. Now, the good point to go to Italy actually is that the history of active faulting is really well understood, both in terms of the timescales and also in terms of the rates by a whole range of different processes. And in the central Apennines, that I'm going to start with, we know these faults are around 3 million years old, and then around 750,000 years ago, they increased, or some of these faults increased their rates due to fault interaction within this fault array. And I'm particularly going to focus on this red fault, this Fiumignano fault, that increased its rate by a factor of 750,000 years ago. And this is something that somewhere where I worked actually a few years ago when I was a PhD student. Here is the fault, and actually we're going to focus on the landscape upstream of that active fault. There's the river comes down through here through this gorge. As I say, the slip rate increased by a factor of 750,000 years ago. And at the time when I was first concentrating on this kind of work, we were really focused on the size and scale of the nick point upstream of the fault. And that was really the kind of key thing that we were looking at. But in fact, more significant in some ways in a geologic context is actually this thing that I'm highlighting here, this huge area, incised area upstream of the fault and downstream of the nick point. This is like the geologic reality of those models I've just been showing you. And that is basically where a lot of the sediment is coming from. So for example, if I look at these valley cross sections between B and C, you've got these V-shaped valleys with hill slope angles of 30 degrees or more. And actually, when you actually look around here, there's landslides, there's squee cones. The hill slopes are really responding to this wave of incision driven by this change of fault slip rate. And that has a fundamental effect on the grain size that is released. So this is grain size against downstream distance towards the fault. The fault is here. And I'm particularly looking at the median grain size D50 and a measure of the coarse grain size fraction D84. And actually that increases all the way to the coarse fraction increases all the way to the fault, driven by, at least in qualitative terms in this study, by landsliding. And then of course that coarse material is extracted into the proximal hanging wall downstream of the fault. So one of the key things that we got out of this kind of study was that this transient response to normal fault growth was not just, it's not just in terms of how much sediment you get. It has really different characteristics, and particularly we see this increase in coarse fraction grain size. Now, when we go to southern Italy, here, one of the advantages looking there is that we have a much wider range of lithologies. So in the central Apennines, there's a lot of limestone. In southern Italy, down here in Calabria, we've actually got limestones, but also granite, schists, etc. So one of the things that Duna Roda Beluda and I really worked on was attempting to first actually work out how fast these catchments were eroding, and we used Cosmogenic Beryllium 10 to do that, but we also compiled a whole bunch of landslide maps and also grain size measurements. I'm going to show you some of those things. So we wanted to really understand that part of the sediment gun. So the first thing that we got out of this in terms of landslides and hill slope sediment supply, we could see there's loads of landslides by the faults. If I went back to this one here, the landslides are all of these brown dots, right? They're all concentrated around the faults. And actually what you find is that the sediment supplied by landslides, they're coarser than just you get from bedrock weathering. In fact, they're 20 to 200% coarser. And how coarse they are really depended on what bedrock was landsliding. So particularly these gneisses were producing really coarse grain size supply. Now, of course, we also ended up showing as well that actually if you considered the percentage of outcropping area that actually had landslides, that also scaled with the rock type and the uniaxial compressive strength of the rock, here measured in terms of the Schmidt-Hammer rebound value. So we actually ended up arguing there's a dual control of rock mass strength or sediment supply from hill slopes upstream of normal faults, both in terms of where the landslides occurred, but also in terms of their grain size distribution. And we could also argue, and this second one showed that even the bedrock, that even ordinary bedrock weathering and fragmentation produced coarser grains when the rock strength was greater. So that lithology effect really modulates the sediment gun. Now, in terms of how much sediment we are getting out, well, catchment average erosion rates are really interesting and important for that. We would expect erosion rates to start to balance footwall uplift rates as these faults propagate and grow. So these are 10 Brilliant 10 erosion rates. This is the footwall component of the fault throw rate. And what, this line in here is perhaps like your one-to-one line, if you like. And actually, a lot of these catchments is really interesting. Actually, all these catchments, or many of them, were eroding broadly at the rate that the faults were slipping, and then some we could clearly show where actually they contain nick points, and these are where the nick points have not propagated all of the way up the catchment. They're the ones that are eroding a little bit slower. We could also see the rock mass strength made a difference as well. So particularly these gneiss and schist actually had got lower catchment averaged erosion rates, and that scaled with their bedrock erodibility. And in fact, the answer there is really about understanding how fast nick point propagation is modulated by bedrock strength. And I could talk for a long time on that topic.
Alex, you're 10 minutes now.
Cool, brilliant. I'm doing good with time. So I think that we then need to put all of those things together, right? I've just said you get out coarser grain sizes when catchments respond to active normal faulting. And of course, you get out more sediment as well. So we have to put those two things together, and that's what we've been thinking of. So we can turn catchment averaged erosion rates into sediment fluxes, and we also know the grain size that is being released. And actually, this is the sort of fingerprint then of the sediment gun, that not only do the faster eroding catchments have greater sediment fluxes, but they also are sourcing coarser sediment as well. So this dual control is really important. So in terms of summarizing that part, I would say that the sediment gun that is fired in transiently perturbed catchments has at least 3 effects. You get more sediment out, the sediment mean grain size and the coarse fraction grain size that you're releasing increases, and also the sediment grain size distribution increases. It gets wider, and that matters if you're interested in a whole bunch of stuff, including the generation of stratigraphy. And that's the last point I really want to focus on, because you might think, well, why does it matter if we really understand what this sediment gun, what this flux signal looks like? And that's because it fundamentally determines what we find in hanging wall stratigraphy. So this is a numerical model that I put together with actually colleague John Armitage. Really did a lot of the modeling stuff for this. And we basically got a normal fault here, and we've got a catchment that's responding to tectonics upstream that's not on the page. And these colors represent the predicted grain size in stratigraphy. We run the model to a steady state, and then we increase the slip rate on the fault by, in this case, a factor of 5. And we also model the increase in grain size that's coming out that scale to the kinds of data that I have already showed you. And actually, what we get in stratigraphy is really interesting when we do this, because when you first increase the fault slip rate, you create accommodation instantaneously, so you've got more space to put the sediment in. But the catchment supplying that sediment perhaps takes 1 million years to adjust to that process. So you do put in some coarser sediment. These are these blue things in here, but the sediment finds very rapidly into the basin because the volume is not enough to fill the space available. So you can end up with these counterintuitive results where on the same timeline, you might get coarsening stratigraphy near the fault, that's in our synthetic borehole A in here, and fining away from the fault. So that really, really matters. So I think that not only does firing this sediment gun really modulate geomorphic responses to normal faulting, but it also plays a crucial role in determining hanging wall stratigraphy. So I'm going to finish with my conclusions, which are that we are beginning to understand how the sediment gun is fired and how it couples tectonics and grain size release. Volume and locus of sediment export from rifted settings is really controlled by the fault growth and interaction. Drainage network evolution is really important there, and Patience Cowie did a huge amount of work on that. Grain size is a key thing in this. Grain size characteristics are coarser, while catchments transiently respond to tectonics, and they could be coupled with the volumetrics. And all of this process is modulated by landsliding and lithology and can control basis stratigraphy. So thank you very much.
Thanks a lot, Alex. There's time for a few questions. If you have one, just type it in the chat, or if you don't have time, then also just type in Q. Gianreto, I know you have a question. You can start.
Okay, Alex, very good talk. My question is actually, do you have an idea how that this system would work if you are below sea level?
Do I have an idea about how this would work if you are below sea level? So do you actually mean in a marine setting, or do you mean
Exactly,
below sea level on land?
Would you also expect to have this sort of erosion, or because actually in the Alps, under marine
Okay, so I think in marine settings, actually, I've actually mostly worked on nick point propagation in submarine fold and thrust belts when we've been working on seismic data off the Niger Delta. And in fact, submarine channel dynamics is actually are quite different from rivers, not least because you can't basically model that using a stream power erosion law. But you know, you can still use an advective diffusive sort of model, and you do get generation nick points upstream of faults. So you get some of the same effects. But you know, in the end, the response that I was just demonstrating here is controlled by the erosion and geomorphic processes that are going on, and they're very different in terrestrial settings from marine settings. So, you know, is the marine sediment gun the same? The answer is no.
Okay, thanks.
There's time for other questions. So far, I can't see any in the chat. Just answered all of them. I would be wondering whether you can use all the information that you have to invert for the evolution of slip rate on the normal fault.
Yeah, the inverse problem. That's a really good question, Sasha. The inverse problem is, you know, is the interesting one. So the inverse problem, in terms of doing this with river long profiles, people are already on. My colleague Gareth Roberts works on this, Liran Gorana has worked on this. There's a lot of people who've done that. The problem is that inverse problem is fine for today, but not so good if you want to work out the history of normal faulting where you don't have the catchments preserved. Then you have to solve that problem from a stratigraphic perspective. And I do think that we can do that at least in a semi-quantitative sense from looking at stratigraphy. So for example, the model I just showed you was based on grain size finding in stratigraphy. But I think the question is, you know, it's challenging because you've got to understand the time constraints. What I would say is that it's very tempting, you know, and if you read classic literature, people say things like, oh, there's an influx of coarse sediment into the basin now, that's when the normal faults really, you know, it's rift climax. But that's not actually true. Probably when the faults really got going, that's the bit where it seems really quiescent, because there's this lag time before the catchments that source sediment are really eroding and bringing that material in. And those are the kinds of insights that I think are really important with this.
Excellent, thanks. Luke Wetmore.
Yeah, hi Alex, so it's a great talk. So
hey,
just
one
question. Yeah, you had I think it was a 5-time increase in slip rate in your model in the sort of penultimate slide. Like that's quite a big increase in the slip rate on a fault. So with maybe more sort of maybe realistic increases in the slip rate, would you still be able to sort of detect the sediment response in terms of the grain size?
Yeah, you would. So that I mean, that one was models in an extreme case for, say, the Fucino fault, for example. But if we did this with a throw rate enhancement factor of 3 or something, that might be reasonable. And we have a whole bunch of model runs like this, then yes, you get basically the same kind of effect. It's modulated by, in detail, actually. You have to think about the relative amount of accommodation you're generating, and also how coarse the grain size signal is upstream. So lithologically, if you've got, I don't know, gneisses or something like this, which are hard, so the nick point propagation rate is slow, but the sediment that's supplied is coarse, then you can end up in this world where the faults speed up. It takes a long time for the landscape to respond, but the sediment that is coming is very coarse, and then you get a very distinctive stratigraphic signature.
Okay.